A very good morning all of you. In today's lecture we are going to discuss how to design the up down counter in the same circuit. That means you are going to use same circuit for designing up and down counter, and after that we are going to design the counters with positive edge trigger and negative edge trigger. So when you change the triggering mechanism, what kind of change you are going to observe, that will be discussed in today's lecture. Then we are going to see how to design the different mod counters. Like you can count only to a certain number, like 0 to 6, 0 to 9 or 0 to 10, whichever the number you want, you can design to certain number. And finally we are going to design the counters with the D flip-flop. Still now whatever we discussed with JK flip-flop or T flip-flop, now we are going to discuss counter design with the D flip-flop. This all for today's lecture coverage. A very good morning all of you. In the last lecture we have seen how to construct the up counter and down counter using either T flip-flop or a JK flip-flop. Now I am going to construct a circuit where you can design both up and down counter in the same circuit. So let us just redraw the up counter and down counter, then we will try to construct the up down counter in the same circuit. Look at here, we are going to construct 2-bit up down counter. We are going to construct 2-bit up down counter. So we are going to use two flip-flops. So this, let's say, T flip-flop, this is also T flip-flop, and this is the clock, and this is the clock for the second T flip-flop. Now this is up counting. Similarly, if you take two flip-flop here, and if I give clock from this input to second flip-flop, this first T flip-flop, this is second T flip-flop, and this is clock, and this here down counting circuit. Now I am going to merge these two. So when I merge, I cannot give clock from both the inputs. What I am going to do is I am going to use one OR gate and with extra AND gates. Okay, that we are going to see that circuit is called up down counter. Now let's take the first flip-flop. Let's take the first flip-flop here, then second flip-flop here. Now I am going to use one OR gate here. This OR gate output is going to be a clock for the second flip-flop. This is one T flip-flop, another T flip-flop. Now I am going to use one AND gate here and one more AND gate here. This Q is connected to this AND gate. Similarly, Q bar is connected to this AND gate. This AND gate output is given to this OR gate, and this AND gate output is given to this OR gate. At any point of time, only one of these gate will be activated. Let's say this is G1, this is G2. So either G1 will be activated or G2 will be activated at a given point of time, depending on the second input. That second input we call it as a control input. This is my M or control input. So the same M I am giving with a NOT gate to the second AND gate. So this is my control input. Now, or you can keep bracket M. Here is my Q1 and this is my Q0. If M equals 0, your gate 2 will be activated and gate 1 will be deactivated, because if M equals 0, this will produce 0 output here. If it's 0, this 0 becomes 1 here, this will be 1 here. So whatever the Q0 bar that will be applied through this AND gate and will be passed through this OR gate and goes to the second flip-flop as a clock. So in this case, is going to do the up counting. If you look at here, when Q0 bar goes as a clock to the second flip-flop, it will be up counting. Similarly, if M equals to 1, your gate 2 will be deactivated and your G1 will be activated. That means this gate will be deactivated. That means you are going to have 0 here. So this becomes 0 here. But if you look at here, this becomes 1 here. Then whatever the Q0 that pass through this AND gate and pass through this OR gate, finally apply the clock to the second flip-flop. In this case, going to be down counter from the previous class. If you look at here, this is a down counting circuit and this is a up counting circuit. The only difference is if Q0 bar goes as a clock to the second flip-flop, it will be up counting. If Q0 goes as a clock to the second, it will be down counting. So by using M value, you can either use the same circuit as for upwards counting or downwards counting. Now we are going to simulate the same circuit and try to show you how your circuit going to count downwards and upwards with the same elements with a extra control input in a moment. Now we are going to see the up down counting circuit simulation. As you can see, you have two JK flip-flop or T flip-flops which are connected to the control input, which can be 0 or 1, but usually when counting process takes place, you are going to keep J equals to 1 and K equals to 1. And this is my control input. For this control, if you look at carefully, your NOT gate is connected to the lower end gate and normal output is connected to the second end gate. And first, if you look at the top end gate is connected to the Q and bottom end gate is connected to the Q bar, and the output of these two end gates is connected to OR gate and applied as a clock to the second flip-flop. If I keep my M equals 0, this 0 becomes 1 here and lower end gate will be activated. That means Q0 will be activated. It's going to be up counter. If M equals 1, the upper end gate will be activated and your Q will be applied as a clock to the second flip-flop. It will be down counter. So up count down can be verified by checking the output of Q0 and Q1. Now I'm going to run the simulation and let's check whether it is going to do the required operation or not. So let's reset the outputs to 0. Now your output 0 0. If I press, if you look at here, my M equals 0. If I press J equals 1, K equals, it's going to count the upwards counting. 0, 1, then 2, then 3, then 0 0. So if you look at here, my J equals to 1, K equals to 1 and my M equals 0, it is counting in the upward direction. So let me keep J equals 0, K equals 0. Now it is 0 0. If I'm going to make my M equals to 1 now. When M equals to 1 is supposed to count to the downside. That means 0 0, then followed by 1 1, then followed by 1 0, then followed by 0 1, then 0 0 will come. Now we'll try to see downwards counting. So now both become 1 1, then 1 0, then 0 1, then 0 0, again 1 1. So now it is counting in the downwards direction because your Q is applied as a clock to the second flip-flop. So this is how you can construct a 2-bit up and down counter. Similarly, the same idea can be implemented to the 3 bits that we are going to see in a moment. Now let us simulate the 3-bit up down counter. As you can see, there are 3 flip-flops for the 3 bits. And you can see this circuit is same, 2 AND gates followed by OR gate, 2 AND gate followed by OR gate. This small circuit will enable either Q will be applied as a clock to the second flip-flop or Q bar will be applied as clock to second based on the control line. If you look at it, this control line is connected through a NOT gate here. The same it is connected to the second AND gate. That means lower AND gates are connected through NOT gate and upper AND gates are connected directly to the control line. Okay, that means when M equals to 1, you are going to enable the upper AND gates, and M equals 0, you are going to enable the lower AND gates. That's nothing but when you M equals 0, your Q bar will be applied as a clock to the second flip-flop. Here also Q1 bar will be applied as a clock to the third flip-flop. It means going to count in the upwards direction. Similarly, when M equals to 1, it is going to count in the downwards direction. Now we'll run the simulation and try to verify its working. Now I'm going to clear all the inputs to Now I'm going to clear all the outputs to 0. Now you can see all are zeros. Now I'm going to first count in the upward direction, so I make my m equals 0. Now I'm going to keep my j equals to 1 and k equals to 1. Now you can see it's going to count in the upwards direction now. 0, 1, 2 till 7, then it goes to 0. Then 0. This is upwards counting. Now I'm going to show you the downwards counting. So let me make j equals 0, k equals 0 to make it in the memory state. And clear. I'm going to keep my control as 1. So in this case I'm going to count from downwards direction. That means after 0 you're going to get 7, then 6, then 5, so on. Let's run. Let's make it j equals to 1 and k equals to 1 to run the counting process. Now you can see 7, 6, 5 and so on. So this same circuit can be extended to 4-bit by adding one more flip-flop and one more 2 AND gate, 1 OR gate circuit. As usual, connecting preset, clear all those inputs and connect to a BCD to 7 segment display. You can count from 0 to 15 and 15 to 0 with the same circuit. So this is all about your upward, this is all about your up down counter using same circuit. Now we are going to design the modulus counters, where we are going to count only a certain number. After that your counter going to reset to 0 0 state. So till now we have discussed how to construct up counter, down counter and up down counter. Now we are going to see how to design asynchronous counters, or simply I can say a modulus counters. Modulus counters are special counters where we can define the counter outputs, like till how many states counter should count. Suppose if you take a 4-bit counter, which is going to take 0 0 to F, that means 16 states. Okay, instead of 16 states I can restrict my counter to only 10 states. In that case that counter is called mod 10 counter. If I restrict to only 6 states, I can call that as a mod 6 counter. So mod 6 counter means it can count from 0 to 5, total 6 states. Mod 10 counter means it's going to count from 0 to 9, total 10 states. So that's how we can restrict our counter settings to a desired counting number. It can be 6 or 7 or 9 depending on our requirement. Now we'll try to see how to design those counter and how to reset your output to the a particular state whenever it reaches a desired output level. Okay. So let's start with mod 6 counter for the simplicity. Mod 6 counter means total 6 states. That means 0, 1, 2, 3, 4 and 5. Total, if you look at, these are the 6 states. After 5th state, come back to 0 state. So you are going to design a counter which can count through 0 to 5, not more than that. So in order to do this, we need at least 3 flip-flops. If you want to count from 0 to 6, you need at least 3 flip-flops. 3 flip-flop output, let's say assume first flip-flop output is A and second flip-flop output is B and third flip-flop output is C, let us assume for the simplicity. So A is my LSB and C is my MSB. So first we start with 0 0, then goes to then goes to 0 0 1 and 0 0 1 to 0 1 0, then 0 1 1, then 1 0 0, then 1 0 1. So these are the sequence your counter pass throughs. After this it's going to be 1 1 0, but this movement will stay in a only short period of time and goes to 0 0 state. Similarly, if you encounter unexpectedly 1 1 0 also, it's going to be 0 state. So that means it's going to count only from 0 to 5, only this much. This is 0 and start from 1, then 2, then 3, 4, then 5, again 0. If at all encounter any of these, if it encounter any of these two input, goes to the 0 0 state, or after 5 momentarily your counter goes to 1 1 0 and it sets to 0 0 in a fraction of second. That we are going to see how we are going to design that. Let's take 3 flip-flop, flip-flop 1, flip-flop 2 and flip-flop 3. This output is A, and this output is B, and this output is C. Now we are counting up counting in asynchronous, so that means your Q0 bar will be act as a clock to the second flip-flop, and your Q1 bar will act as a clock to the third flip-flop, and your clock will be as usual. Now your ABC will produce your output. A, B, C will produce output from 0 0 to all ones in practical situation. But we are going to do a small modification. The small modification will count only 0 to 5. What we are going to do? We are going to add one extra NAND gate here. For this NAND gate, if you look at here, it goes from 0 0 to 0 0 1 and 0 1 0, 0 1 1, then 1 0 0, 1 0 1, then it goes to 1 1 0. So if you look at here, your B and C are 1 1 in the 6th, that means 7th state. So whenever it goes to the 7th state, that means 1 1, that means B is 1, C is 1. I'm going to connect my B and C output in AND gate. When both are 1 1, you are going to see output as 0 here. For any other condition, this output will not be 0, because if you look at here, this condition will be produce 1, this condition will produce 1, this condition will produce 1, and other conditions, except your 1 1 condition, all other combination B and C producing 1 output. Whenever your B and C are 1 1, you are going to produce 0. This 0 output I am going to give as a clear for all the flip-flops. I am going to give my output of AND gate output of B and C. So this is my clear output for each flip-flop. So whenever B and C goes to 1 1 state, your AND gate produces 0. This 0 will clear outputs. So after this pulse, it going to all 0 0 state. So this is my LSB and this is my MSB. So this is how, whenever counter goes to an undesired state, which we don't want, we are going to add an extra circuit. The circuit will produce a reset signal or clear signal to the flip-flop, so that goes to all 0 states. Now we will try to verify the same circuit using DIT software in a moment. Now let us simulate the mod 6 counter. It is same as your 3-bit up counter. Only difference is I added one extra NAND gate here. This NAND gate output will be given through one more AND gate through the clear input. If you observe, if you keep clear equals 0, this AND gate output will be 0. You are going to clear all your output. This is a regular operation. When you keep clear equals to 1, whenever your Q2 and Q1 are whenever your B and C are 1 1, this NAND gate output will be 0. This 0 will produce the output of this AND gate will be 0. This 0 again clear your flip-flop. So that means you are going to clear your flip-flop output by two modes. One by direct clearing, one by whenever your output encounters B and C equals to 1. This happens moment when you encounter the 6 counting. Like 6 count is nothing but 1 1 0. So momentarily your output goes to 1 1 0. At the same moment your NAND gate produces 0 and it clear outputs to 0 0 0. So that means your counter going to count from 0 to 5, then it goes to 0. So let's start. Now I kept my flip-flop outputs to 0 0. I'm going to keep my clear to 1, Now I'm going to start j equals to 1 and k equals to 1 for the counter operation. Now if you observe carefully, 1, then 2, then 3, then 4, then 5, next will be 0, not 6. So you can see clearly it went to 6. That means it is counting from 0 to 5 or 6, total 6 states, and it is excluding 6th and 7th, that means 7th state and 8th state. So that's how we can limit our counting number from either 0 to 5 or 0 to 4, depending on how you are going to clear the flip-flop or at what moment you are going to clear your flip-flop to the 0, 0 state. This is for mod 6. Similarly, we can design for mod 10 counter that we will see in a moment. So let's see the mod 10 counter. In case of mod 10 counter, we are going to use 4 flip-flops, because if you want to count from 0 to 9, total 10 states. Please remember, mod 10 counter can count 0 to 9, total 10 states. Sometimes you call it the decade counter also. We say why it is called decade counter in later part. So if you want to count 0 to 9, you need required 4 flip-flop. That means 4 flip-flop output start from all zeros. Let's say this is my A, B, C. These are the output of my 4 flip-flops. So you're going to connect 4 flip-flop like whatever you have seen previously, and your flip-flop output goes from 0, 0 to 0, 0, 1, then 0, 0, 1, 0 till 1, 0, 0, 1. That is nothing but 9. After 9, the momentarily your after 1, 0, 0, 9, it's going to momentarily it goes to 1, 0, 1, 0 state. At this place, you are going to have a B equals to 1 and D equals to 1. So what you are going to do, you are going to connect B and D. You are going to connect B into a NAND gate. This NAND gate output produces 0. This we are going to keep it as a input to the clear of the flip-flops. So your B equals to D equals to 1 will happen only at 10, and B and D equals to 1 will never happen when you count from 0 to 9. So we are going to use one NAND gate. NAND gate will be connected by B and D inputs. This will produce a low output whenever your B and D equals to 1. This happens only when you encounter 1, 0, 1, 0 at the output side, and it's going to clear all the outputs to 0, 0. Now we are going to see the same circuit. This is your mod 10 circuit, which will count from 0 to 9 and will have a total 10 states in a moment. Now this is your mod 10 counter, which will count from 0 to 9. It is having 4 flip-flop. Ideally it should count from 0 to F, but it is going to count only 0 to 9. The moment it reaches 1, 0, 1, 0, that means when D equals to 1 and B equals to 1, your NAND gate going to produce a 0 output. This 0 will pass through this AND gate and will apply as a low input to the clear input of the all the flip-flops. Is going to clear all the flip-flops to 0, or else any other condition between 0 to 9, your NAND gate going to produce output 1 and here also 1. So it will be 1 state. So your JK flip-flop will not be disturbed. Suppose if you want to manually clear it, you can make this as 0. So this AND gate produces 0 and this 0 will clear all the flip-flops. So by this way you can either clear your flip-flops by using clear input, or whenever your output of the flip-flop goes to 1, 0, 1, 0 state. So that means you are going to count only 0 to 9. Let's run the simulation now. I cleared my, let me clear my outputs. So now all the outputs are 0, 0. You can see 0. Now I'm going to make my clear to 1. Now my J and K are 0, 0. I'm going to make my J and K to 1 now. The moment I keep J equals to 1, K equals to 1, my counter start count from 0 to 9, then goes to 0. Let's have a look. 1, then 2, 3. You can also check the binary equivalent is producing at the output of the all the 4 flip-flops. 7, then 8, then 9, and goes to 0. You can see 9, after 9 it goes to 0 because your NAND gate going to produce a 0 here. This 0 will clear all the flip-flop outputs to 0, 0. Now again, once again we can check. 6, then 7, 8, then 9, then 0. So this is how we can design the counter according to our convenience, whether we want to count only 0 to 5 or 0 to 6 or 0 to 9 or any other arbitrary number. So this is what is meant by designing modulus counters. So till now we have discussed your counters with only positive edge triggered clock or positive edge triggering. Now you are going to see how when you change the clock triggering from positive edge to the negative edge. So if you look at here, when you go to the DEET software, where you can find positive edge triggered and negative edge triggered. So what you do is open the DEET software, go to flip-flop station. If you look at it, this PET is nothing but positive edge triggered and NET is nothing but negative edge trigger. When you take a negative edge trigger, you are going to see the bubble here. When you take the positive edge trigger, you don't see any bubble here. So that's the major difference between positive edge trigger and negative edge triggering flip-flops. That means there is an inbuilt positive edge triggering circuit here and inbuilt negative edge triggering circuit for this particular flip-flop. The clock will be same as usual. So when you design counters with positive edge triggering, we have seen when you connect Q bar as a clock for the second flip-flop or next flip-flop, we have seen up counting. Similarly, when you connect Q as a clock to the next flip-flop, whether it may be 2-bit or 3-bit or any number of bit, you are going to see the down counting. So this we already verified. When Q bar is connected, it is counting in upward direction. When Q is connected as a clock to the next flip-flop, it is counting in the downwards direction. When you, in case of negative edge triggering, suppose when you use instead of positive edge triggering, it will be opposite of this condition. When you connect a Q bar as a clock to the next flip-flop, it is going to count in the downwards direction because your second flip-flop will respond whenever clock goes from 1 to 0. In this case, your second flip-flop will respond whenever clock goes from 0 to 1. So as a result, if your Q bar act as a clock to the next flip-flop, it will be down counting. Similarly, if Q is act as a clock for the next flip-flop, it will be up counting. That I am going to show you in a moment. So please remember only difference is your next flip-flop will respond in case of negative edge triggering 1 to 0 transition, in case of positive edge triggering 0 to 1 transition. This is only a difference you should remember when you design the circuit with positive edge triggering and negative edge triggering. Now we'll try to see the negative edge triggered circuit. Please remember the rule, or please remember this notation. When Q bar is connected to as a clock to the next flip-flop, it will be down counting. If Q is connected, it will be up counting. It is a reverse of your positive edge triggering. Now we'll see the simulation. Now coming to the simulation, this is my 2-bit counter, and if you observe carefully, everything is same except your JK flip-flop. If you look at here, this JK flip-flop is negative edge trigger. You can see the bubble here and you can also see the bubble here. Now if you look at here, my Q bar is act as a clock to the next flip-flop. So in this case, if it is a positive edge trigger, it's supposed to be up counting. Since it is a negative edge trigger, it's going to count in the downwards direction. Now we'll try to simulate and see. Everything is same except only flip-flop change. I'm going to start my simulation. Let's clear it, your outputs to 0 0, then make it 1. Now I'm going to make j equals to 1 and k equals to 1. Now you are going to see the action 0, then 3, then 2, 1 and 0. Now you can see 3, then 2, then 1, then 0 0. So this is down counting. Previously when we used positive edge triggering, it was up counting. This is for 2-bit. Now similarly you can also look for the, so this is for 3-bit, same thing. If you observe carefully, everything is same except your JK flip-flops are negative edge triggered. I am going to clear my flip-flop output first. I am going to clear my flip-flop outputs. Now you can see this is 0 0, and I am going to make my clear 1. Now I am going to keep my j equals to 1 and k equals to 1. As a result, you are going to see the downwards counting. If it is a positive edge trigger, it's supposed to count in the upward direction because your Q bar is connected as a clock to the next flip-flop. Since you are using negative edge trigger, it's going to count in the downwards direction. Let's run the simulation. Observe carefully. 7, 6, 5. It's very clear. It is acting exactly opposite to the positive edge triggered clock pulse. Again 7. So this is for 3-bit. Let's go to the 4-bit counting. Same thing here. I'm going to clear my output to 0, all the 0, then make it 1. Then I'm going to apply my clock. Now counting going to start from F to 0. Let's run the simulation. You can see here 0, after that F to E, then it goes to 0. Let's make a simulation a little faster. Now you can see again F. So this is a down counting circuit, only with a small difference that we have used a negative edge triggered clock pulse. Similarly, if you connect Q as a clock to the next flip flop, it is going to count in the upward direction, that we will see in a moment. Now let us run the up counter using negative edge triggered flip flop. The circuit is same. I have just replaced my JK flip flop with negative edge triggered flip flop. And in the previous case, when we were using positive edge triggered, this circuit is used for the down counting purpose, where Q is connected to the clock as a second flip flop. Whereas negative edge triggered, when Q is connected as a clock to the next flip flop, it is going to count in the upward direction. Now we will run the simulation. Let's clear the flip flop outputs to 0 0. Now I'm going to start my counting with the 2-bit. The moment I keep J equals 1 and K equals 1, is going to count from 0, then 1, then 2 and 3. 1, 2, 3. So my clock frequency is little higher side. Let will make it 5 Hz. Now I can see here 1, then 2, then 3, then 0. So this is for 2-bit. Similarly, when you go to the 3-bit counting, let's clear it my flip flop outputs. Let's make the J equals 1 and K equals 1. Now it's going to count from 0 to 7. 1, then 2, 3. So this also negative edge triggered. Everything is same. Only thing is I changed Q bar to Q as a clock to the next flip flop. This is for 3-bit. In case of 4-bit, let's clear the flip flop outputs. Let's make it J equals 1 and K equals 1. It's going to count in the upward direction. Let's increase the frequency. Now you can see it is counting in the upward direction. Previously, when we were using positive edge triggered flip flops, it used to be a down counting. Now it is in the up counting. So make sure when you design the circuit, please remember in this mind whether your flip flop is supposed to respond positive going clock transition or negative going clock transition. So this is all about your counters with the negative edge triggered flip flops. Now we'll try to see the construction of counters with the D flip flop. Now let us start the asynchronous counter design with D flip flop. So as usual, if you want to, so we'll start with the 2-bit up counter with D flip flop. That means you are going to count from 0 to 3. So 2 flip flop will store 2 outputs. Let's take Q0 as first flip flop output and Q1 as second flip flop output. So initially both will be 0, then it goes to 0 1 state, then 1 0 state and 1 1 state. So your first flip flop has to change 0 to 1 and 1 to 0 and 0 to 1. Since it is a D flip flop, it cannot toggle, unlike your T flip flop or JK flip flop with J equals 1 K equals 1. So to make the toggling action, what we do is we just going to connect your Q0 bar. So both the flip flop Q0 bar as a feedback to the input. As a result, so this is my Q0. So this is my clock. I'm going to apply clock to the first flip flop since it's asynchronous. If you look at here, so this is a positive edge to going transition. So whenever clock make the transition, whenever your Q0 is 0, 1 here, the 1 goes here and 1 comes here. Whenever this is 1, this will be 0, and again the 0 goes here and 0 comes here, and this becomes 1 here. So as long as your clock is applying to the first flip-flop, your Q0 going to toggle between 0 and 1 because of this Q0 bar is connected as a input to the D. Same way, to make your Q2 flip-flop also 0 to 1, you are going to connect the Q1 bar as a input to the second flip-flop. Now as you know, for the up counting you are going to give Q0 bar as a clock to the second flip-flop. In case of positive edge triggered, please remember these are positive edge triggered. So in case of positive edge trigger, if you want to count in the upward direction, you are supposed to give Q0 bar as a clock to the second flip-flop. So whenever your Q0 bar goes from 0 to 1, or whenever Q0 goes from 1 to 0, if you look at here, your second flip-flop is toggling whenever your Q is going from 1 to 0, but your flip-flop is negative, your flip-flop is positive edge triggering. So if you take the Q0 bar output, so this will be 1 0 1 0. So in this case, your Q0 bar is going from 1 to 0, will act as a clock to the second flip-flop, and your second flip-flop will respond accordingly and produce the appropriate output at Q1. So this is how we can use D flip-flop for the counting application. Suppose you want to build a down counter, you can keep everything same. Only thing is you just keep this clock for the second flip-flop to the Q0, rest will be same. Suppose if you want to increase to 3 bit and 4 bit, just add one more D flip-flop, make the same connection. For up counting, you give your Q1 bar output as a clock to the second flip-flop, your Q1 bar output as a clock to the next flip-flop. Similarly, Q2 bar output as a flip-flop clock to the next flip-flop for the 4-bit countings. So we'll try to simulate the same circuit, and we'll try to see how your D flip-flop going to give the counting sequence in a moment. Now if you look at here, this is a counter, up counter, because your Q bar is connected as a clock to the second flip-flop, and I'm using positive edge triggered flip-flop. So this will be up counting, and if you can clearly see my Q0 bar is connected as input to the first flip-flop, and similarly Q1 bar is connected as input to the second flip-flop. So first flip-flop will change its output for each clock pulse. Second flip-flop will change its output whenever your Q0 bar goes from 0 to 1. Let's run the simulation. Let's make my outputs to 0 0 by clear it. Now you can see here now you can see it is counting 1, then 2, then 3, 0 0. So you don't have to give any extra control in one, like your J equals to K equals to the JK flip-flop. For D flip-flop, you don't have to give. It automatically works from there. Let's preset it. So if you look at now, it is at 3. If I make it preset to 1, it's going to counting from 1 1 will be there, then it goes to 0, then 1 2 3, it will be upwards direction. Now you can see it is counting in the upward direction. This is with the 2-bit. Now we'll try to see with the 3-bit in a moment. This is with 3-bit. Everything is same. My Q bar is connected as a clock to the next flip-flop. That means up counting. Now you don't have to give any control input because it is not JK flip-flop, and your inputs are in a closed feedback. Your Q bar is connected as a input to the D flip-flop. Now run the simulation. Let's clear it. Now I clear. The moment I make clear equals to 1, for every clock pulse, your first flip-flop will respond. Your second flip will respond whenever your Q0 bar goes from 0 to 1. Your third flip-flop will respond whenever your Q1 bar goes from 0 to 1. Let's make it clear equals to 1. Let's see the up counting. Let's make my frequency a little faster. Now you can see it is going in the up counting fashion. So this is with the 3-bit. Now let's make it with the 4-bit in a moment. So this is with now let us see the 4-bit up counter using D flip-flops. Now I'm going to clear all the flip-flop outputs. Now you can see all are cleared. You can clearly see my Q bar has acted as a clock to the subsequent flip-flops. Rest all are same. Let's make my clear equals 1. The moment I make clear equals 1, it is going to start from 0 to F. Now you can see it is counting in the upward direction. So this is how you are going to build the counters using D flip-flops. Suppose if you want to count the down counting, what you do is you just change your clock input to the second, third and fourth flip-flops by simply connecting to the Q as a clock to the subsequent flip-flops. You are going to get the down counters. This is all about your counting with D flip-flop. So this is all for asynchronous counter. In the next lecture we are going to see how to design the synchronous counters.